So that brings us to the next proof method, the mathematical induction. Okay, so this is going to be the main focus of the remainder of this class, and we are going to talk about mathematical induction and how we use it to prove theorems. And also based on induction, we are going to see how functions and structures can be defined recursively. And this also ties in with Peano's fifth axiom, the induction axiom. Okay, so in general, as stated here, mathematical induction is used to prove statements in the form for all natural numbers P of n. This will be the general structure, but there might be slight differences in different settings. The principle of mathematical induction, as I said, if you recall Peano's axiom, is stated here if P1 is true and, well, a P is forgotten here, Pk implies Pk plus 1 for all the remainder of integer values, then Pn is true for all n greater than or equal to 1. Now here you see this is the statement in first order logic that lays out mathematical induction. If P1 is true, now this one here is, we will call this the basis or the base case. It doesn't need to be 1. If you remember, I said when we talked about Peano's axioms, it's just a naming. Well, here, of course, it's not going to be just a naming, but it's going to indicate from what point does your proposition P of n starts being true. It could start being true from 10, it could start being true from 0, from 1, from 3. It could be any integer, let's say. But in a general sense, 1 here indicates the first case or the first number that it is true for. Okay, so this statement can be generalizable by playing with this value here, but that's not really significant. Now, this is the basis, and this together with this implication here, for all k values, Pk implies Pk plus 1. If these two are together true, then we conclude that the proposition is true for all natural numbers or all positive integers. Since we start with 1, it will be true for positive integers. If you start from 0, it will be true for natural numbers. If you start from 5, it will be true for integers greater than 5. That's the general picture. Okay, so what we are going to do is 2 steps. One is the basis step, prove P1 is true here. And number 2 is called the inductive step, prove for k values greater than or equal to 1, Pk implies Pk plus 1. Okay, so this part here. If you prove these two, then we will conclude that it's true for all numbers. Okay, the smallest element need not be 0 or 1. Well, this is a slightly different statement here because it's not just the naming here, it's the actual value that is significant, but still the basis step doesn't have to be just 1. Okay, let's see this on a simple example, a classical example, the sum of integers from 1 up to n. Okay, so the formula is n times n plus 1 divided by 2. Okay, how are we going to prove this? Using mathematical induction. Again, remember, there are other methods of proof, so you can use also them. But here, our focus in the remainder is going to be on induction. The basis step, take this proposition and apply 1. And for 1, it's just the sum of integers from 1 up to 1. Well, it's just 1 by itself. So it's 1 times 1 plus 1 divided by 2. That's equal to 1. Therefore, the basis step is true. Okay. Next one, the inductive step. Now here, we are going to assume that the given proposition is true for up to the integers k. Okay, so we are going to assume that the given statement is true for n equals k. Okay, so k is applied here, and this sum is equal to k times k plus 1 divided by 2. Now, this is our assumption in the inductive step, and we will show the implication. When this is true, the formula for k plus 1 follows from this. Okay, to do that, what we are going to do is, of course, we have the sum up to k. Therefore, we'll just add the element for k plus 1. So this is the sum I'm after, and the first k terms is present in the sum, and I'm going to explicitly add k plus 1, and this sum, based on my assumption, I know to be equal to k times k plus 1 over 2. If you add k plus 1 to it and arrange the terms, you obtain k plus 1 times k plus 2 divided by 2. Now, what is this? This is exactly this term here multiplied by that plus 1 divided by 2 as expected. Okay, so this, since based on this assumption, I can reach to this, meaning that P of k implies P of k plus 1. Then, along with the basis step, I conclude that this formula is valid for all positive integers. Okay, here's another example. Here, in this question, you see we do not have an identity. We don't have an equality here. We have an inequality. So induction is also useful for showing inequalities. Show that for all natural numbers, n is less than 2 to the power n. Now, for the basis step, now we are going to start with 0, since the proposition includes all natural numbers and 0 among them. Therefore, we are going to set the basis step for n equals 0, and clearly 0 is less than 2 to the power 0, which is 1. So basis step is verified. In the inductive step, we assume that this holds for the value k. K is less than 2 to the power k. This will be assumed to be true, and we will show that this entails the statement is true for k plus 1. Now, if you add 1 to each side, you obtain k plus 1 less than 2 to the power k plus 1. Now, I know that k here is at least 1, because in the inductive step, I'm looking at the numbers that are greater than the basis step, so it's at least 1. Okay, so this 1 here, if I replace it with 2 to the power k, it's obvious that 2 to the power k for any k greater than 0 is greater than 1. Okay, so if I replace this 1 here with 2 to the power k, this amount is going to become even larger. So this inequality here is going to be preserved. Therefore, k plus 1 is really less than 2 to the power k plus 2 to the power k, which makes 2 times 2 to the power k, which is equal to 2 to the power k plus 1. So what I obtain is k less than 2 to the power k implies k plus 1 is less than 2 to the power k plus 1. Hence, along with the basis step, this entails that for all natural numbers, this inequality holds.